I had to pause that for a second because I got a little lost in myself. But yeah, it's going to make water and it's going to make barium sulfate. Excuse me, barium sulfate, which would be your solid. Now, on the opposite side of the equation, I do realize that we've got this hydrogen sulfate, but you have sulfate on the other side. They're still going to exchange and do a double replacement reaction, but you write the weak acid, which in this case is the HSO4 minus, together. And so this would be not quite balanced. I need 2 in front of the water, plus sign there. And so it would look like this. Water could be labeled here as a liquid as well. So just going down here and looking at, the answer here, yeah, this is what it is right here. Probably should have labeled this a solid, labeled this a liquid as well. Yeah. Going to the next one, hydrogen sulfide gas is bubbled through excess potassium hydroxide. You'll have H2S as a gas, and that is going to produce, that is going to combine with potassium hydroxide KOH. And what it's going to make is KHS actually, and H2O. So what happens is the hydrogen sulfide would be left together because it's a gas. The potassium hydroxide would be ionized. The potassium will be ionized on the other side with something, the hydrogen sulfide anion left. And then of course, water being a liquid left over as well. You would cross out the potassiums and then you would have your net ionic equation there. Little strange. It's just like the single dissociation for the sulfuric acid. These weak acids are going to dissociate a single hydrogen ion before they dissociate the second one. The only one that we're really worried about that second dissociation is sulfuric, and we'll talk about that again later. S2 minus is not a thing. It's always HS minus. So watch out for substances that react with water to actually make the acidic or basic substance that you're talking about, which is interesting. And we did this a while back, but it's been a few moons since we did it. But you have sulfur dioxide gas is bubbled through an excess solution of calcium hydroxide like this. But I don't see the acid there. The reason I don't see the acid is because I'm not paying attention to the solution. H2O and SO2 actually make H2SO3. So when I do this double replacement or this neutralization reaction, what I'm going to use is that H2SO3. So what I'm going to end up making is this sulfite is going to go with the calcium. So I'm left with calcium sulfite, which is a solid. And then I'm left with my 2 moles of water as well. If I go back and kind of X my stuff out and look at this here, what I would do is take away the H2SO3 and I'm left with this equation. So you have to kind of make the acid, do your double replacement, predict your products, and then kind of take it away is kind of how I do it. Now I've got excess water on both sides, so I can get rid of the water on this side, get rid of the 2 on the other side, just have 1 mole of water, and I'm left with the sulfur dioxide, the calcium hydroxide, the calcium sulfate, and so forth. If I do it this way, I could then go and get rid of spectators. I didn't ionize any of this. Calcium hydroxide can be written kind of either, to be perfectly honest. It does say a saturated solution of calcium hydroxide. So all of it is ionized. There isn't really any solid in there, but you can write calcium hydroxide together or separate actually, or the original rules that we don't really have to worry about anymore since you won't have reaction prediction on your actual AP test. But I would write it like this. Why did I use a parentheses? It's interesting. Calcium sulfate, which is the solid precipitate, and then of course water is the liquid that's also formed. It would look like this. And if you check, it's fully balanced. We don't look at my answer here. It's written here. Labeling this a solid would be good. Labeling this a liquid would be good. And of course, the sulfur dioxide was a gas as well. Would be a better way to label it. But you could actually leave the calcium hydroxide together and write it as aqueous. It doesn't ionize quite as well as the heavier 2A hydroxides of strontium and barium, but it's okay. It's okay to write it that way. So neutralization reactions are when you add that acid to a base, it will make a more neutral solution, depending on what you add and the amounts that you add. But generally what happens is you add an acid and a base together and you get a salt, an ionic compound, and water as your products. And what we say is, this neutralizes the acid, but essentially you're making a more neutral solution than you had originally. So the way we do this is with titrations. And so what you'll use is a burette. Generally in the burette right here goes your known your known concentration. Not always, though. The first lab that we do here, we do a standardization of NaOH, and we actually use the known is our potassium hydrogen phthalate, which is actually in the beaker or in the flask. That's unusual because we were standardizing the sodium hydroxide solution. But usually, and from this lab forward, when you use your standardized sodium hydroxide, you'll actually put it in the burette. You won't put it in the flask. And so you do this. Now, if you look here at this particular titration curve that I'm tracing here, when you add an acid to a base, they're both strong. You're going to end up with a pH of 7. Now, that's not true for all graphs, right? I mean, if you had a weak acid with a strong base, it would actually start with a higher pH if it was a weak acid, and it would come up like this. So you would actually have an equivalence point that's a little bit higher. And we'll talk more about this in the next unit in a little bit in our labs this week. But you can have some different looking curves, but the same thing is true. At that midpoint where the slope is the greatest is where your equivalence point is going to be. So there's your titrant. That's the solution that you know. Usually it's in the burette, 90% of the time it's in the burette. And the equivalence point is going to be where you have the same number of moles of acid as moles of base. It's also called the stoichiometric point, means the same thing. It's where your moles of acid, moles of base are the same. It can coordinate with your indicator if you actually choose the appropriate indicator. In this case, we've got thymol blue, which changes at a pH of about 9. And then we've got methyl red, which changes at a pH of about 6.625 or so. Those are really not appropriate indicators to use for an equivalence point of 7. Bromothymol blue changes from yellow to green, going up in pH, and then turns blue in a base. That would be a better pH indicator at 7. But you need to choose the correct indicator so that your end point, which is the point where the indicator changes color, matches up with your equivalence point in order to use the right indicator for your titrations. These two are really not the right indicator for this one. So the last thing, this is the last thing here. And I'm just flashing this up here. I apologize, but you guys are going to do this is just a straight up titration. You're given a certain amount of milliliters of perchloric acid that you use to neutralize the 25 milliliters of NaOH. You're trying to find the molarity of the NaOH. The stoichiometric way is a very easy way to do it. You can also use Navier-Nubvup, and I'll explain that in a second, but you want to make sure you don't actually use your M1, V1, M2, V2 calculation.